Hi, my name is Melissa Foley, and this is Lab 2, Lines of Charge. In this video, I will introduce the lab, explain assumptions made, major concepts used, the experiment itself, and a computational model to go along with that. I will conclude with the results and remaining questions about the lab, as well as a conclusion. This lab was about understanding how an evenly distributed charge can influence objects, how to predict the sign of an object's charge based on observation and reasoning. From this, calculations can be used to quantify values like the electric force, charge, excess and deficit electrons on an object, the number of atoms on an object, and even the ratio of atoms to electrons. Some major assumptions that were made in this experiment was that each piece of tape is exactly 20 centimeters, not 19.9, not 20.1, exactly 20 centimeters to the atom. The surface of the adhesive is 1 atom in thickness and is uniform. The system is isolated from external charges or sources of charge dissipation. The fact that you can treat a U-tape as several point charges, and the assumption that each U-tape has the same amount of charge evenly distributed along the length of the tape. Some major concepts used are the conservation of charge, and the fact that the electric charge in a system is isolated and will not change. Newton's second and third laws, the sum of all forces on an object equals its mass times the acceleration of the object, and that each force has an equal and opposite force. The superposition principle. The electric field of one object is unaffected by the presence of another charge nearby. First in this lab, a charge tape was made. To do this, a base layer of tape that is 20 centimeters in length is stuck to a tabletop. Next, another 20 centimeter strip of tape, labeled a U-tape, is layered on top of the base tape. Then, to charge the U-tape, it is pulled off the base tape and held only by its end so that the charge is not dissipated by touching other objects. As seen, the tape is attracted to my hand. When two U-tapes are made, they repel each other, which leads to the conclusion that each U-tape carries a similar charge. In a given example, a plastic pen is rubbed in hair and is negatively charged. From this, the sign of the charge on a piece of U-tape can be observed. Since it's known that a pen carries a negative charge, the tape must carry a positive charge for them to be attracted. A second part of this lab involves creating one U-tape and securing it between two objects. I used two glasses. Then, after creating a second U-tape, put it underneath the first to cause it to float in the air. Newton's second and third laws help explain the physics behind this. An extended free body diagram can be created from this. The electric force from the bottom tape on the top tape points upward. Once the top tape is at a point where it stops moving, it's in equilibrium. The force of gravity equals this electric force and points downward. The distance I measured where this occurs was at 4 centimeters separation distance. Through further calculations, the force of gravity on the top tape has a magnitude of 0.00196 newtons. From this part of the experiment, a computational model can be created. The line of red point charges represents the top tape, and the blue represents the bottom. In this model, the white arrow and the yellow arrow are of equal magnitude. The white arrow represents the net electric force upward, and the yellow, the gravitational force on the top tape, pointing downward. The green arrows represent the electric force distributed across the top tape. As you can see on the right, the magnitude of the electric force, the white arrow, and the yellow arrow, the gravitational force, equal each other in magnitude. Additionally, when this model is viewed from another axis, it looks similar to Lab 1. This has helped me understand that the major concepts from Lab 1 still play a role in Lab 2. However, our visualization of the experiment has changed to allow our calculations to be closer to the real value of the charge Q on the top tape. Some remaining questions. What if each tape was a single point charge like in the previous lab? Compare the charge values in each experiment. The main difference I saw was that the point charge was less than the line charge. Why do these estimates differ? Which is more likely to be closer to the real value? These estimates differ because they rely on different basic assumptions and equations to lead to the value of charge. In the point charge equation, the assumptions made reduce the experiment down to its basic form, where in a line charge, this reduction is much less. Because of this, the line charge model is more likely to be closer to the real value, and therefore more accurate. Overall, with the assumptions made and the models used to analyze the results of this experiment, the conclusions that were made align with the major physics concepts that relate to what we were doing in this lab. Some sources where error is likely to occur is in the handling of the U-tape, or if it's handled too much, it can affect the overall charge of the U-tape. This would change the amount of charge, the ratio of electrons, the distance needed to float a piece of U-tape, and the electric force on the top tape by the bottom tape. Thanks for watching.